In this video, I'm going to go over the solution to drawing the Thiessen polygons, which are used to calculate the average precipitation over this particular watershed. It's kind of a heart-shaped watershed with 4 rain gauge precipitation recording stations. And we do this by first drawing. I'm going to do this freehand, by the way, and this is all I expect you to do. I know you could do it if you had a ruler and you had right angles, and you could do this real carefully, and that's the way a computer could do it, and I'm not going to ask you to do that. So what I'm going to ask you to do is to be able to sort of sketch these freehand. I know it won't be perfect, but at least will give you an understanding for what the method, how the method works. So the first thing we do is we're going to draw lines between these straight lines between these different stations. I'm going to draw them in yellow so that they're not too conspicuous, because these are not the Thiessen polygons. So I'm going to draw A to B. I'm going to draw A to C here, C to D, B to C. These are pretty good. Oops, not bad. Now here I have a choice, right? I can draw A to D or B to C to divide this into triangles. My goal is going to be to divide it into triangles. In general, I'm going to pick the shorter line. So if I drew AD is going to be shorter than BC. So I'm going to actually use this line here. So that's supposed to go right to D. All right, so now that we've drawn our lines connecting the stations, the way we draw the Thiessen polygons is we are now going to draw the perpendicular bisectors to those red lines. I'm going to draw those in red. So I'm going to try to find the middle. Again, I'm sketching this as best I can. I'm going to draw a line that's perpendicular to that bisector. And one thing that I should find to be true is that these should actually, all 3 edges of the triangle, the perpendicular bisectors, should actually meet in the center at a point. So again, I'm sketching this, but you can sort of see, there they go. This is supposed to, it should have gone down a little farther than that. And then this point here will be where this is the bisector to here, right? And then there should be a bisector down here. It looks like that too. So this is probably a little bit over to there. Again, I'm sketching this. This is not exact. If you took a ruler to it and a right angle, you could do this exactly. But this is all I expect you to do. So now I'm going to extend these perpendicular bisectors, these lines here. They're supposed to be straight. If you had a ruler, you can definitely make them straight. I'm going to extend them all the way to the edge of the watershed. It's supposed to be a straight line. Okay, so those red lines represent the boundaries between my Thiessen polygons, and so this works. This is not so bad. And the way this works is then I have defined which parts of the region of the watershed are going to be represented by recording stations at A, B, C, and D. So for example, anything in this, let's make this bigger, anything in this area here will be represented by A. So whatever value for the precipitation I measured at A, I'm going to apply it to everything in this area in blue. And anything that I get for the recording station at C, it's going to represent this portion of the area of the watershed, everything within this polygon there. D is going to be the largest one right here, like this, right? This is everything in here, including way out here, far from the actual recording station. We're going to assume that value of precipitation is whatever we measured at D. So this D is the largest region here. You can see that D commands the biggest area here. And well, actually, it's pretty close, isn't it? B is pretty big too. And B, we'll color B in gray. Why not? So gray, this is B. So B has a funny shape here, but this is all of this region here will be represented by B. So having drawn the Thiessen polygons now, the way we then go and calculate the average precipitation over the watershed is we do a weighted average of the values measured at A, B, and C, D, weighting them by the fraction of area that they control. So what I would do in real life is I'd go find some way of actually measuring these areas of A, of the blue, the green, the pink, and the gray, the areas that are represented by A, B, C, D. And that's what is shown on the next slide. So here I've got the stations. This is the values of precipitation measured at those stations, and these are the areas. I just sort of estimated, did some kind of estimate based on the solution I showed you over here. So the way we compute the weighted average, I'm going to call the weighted average, or the mean the weighted average, is defined as, I am going to take the sum. If you're not good at math symbols, don't worry about it. We'll talk about that, what it means in a second. The sum over all of the areas of the precipitation measured that's representative of that area times the weight of that area. And the weight of an area is defined as its area divided by the total area. So let's give an example, because this may be a little abstract. So the first station A, that was the blue one, right? At A, we measured 47 inches of rain a year, and it had an area of 2.2 square miles. Now, we need the total area. So what we need to do is add up all of these values here, okay? And when I do that, I get 11.5 square miles. So the total area is 11.25 square miles. The weight, again, is defined as the area of this particular partition divided by the total area. So it would be, in this case, 2.2 square miles divided by 11.5. The next one's going to be 5.8 divided by 11.5. And you might be thinking, hey, this is something Excel could do really well, and you'd be right. So this turns out to be 0.191. In other words, that's about 19%. So this blue area here is about 19% of the total area. And I'm going to fill in the rest of these then using the same calculation, the polygon area divided by the total area. So there are all the weights. And one of the ways to check and see if you've got all your weights correct is when you sum the weights, that should sum up to 1. And if I do this, I in fact get 1.000. So I've done it correctly. The next step is to take the weight. Let's just make this clear. I'll take the weight here, and I'm going to multiply that by, so 19% by area, I'm going to multiply that by the value of precipitation I measured in that area. So I'm going to take 0.191, 19%, times 47, and that will be the contribution to the total average from that polygon. And that is equal to 8.61 inches per year. And I'm going to do the same thing then for all the other stations, all the other polygons, B, C, and D. There they are. And now I'm just going to add them all up. And if I add up all of these things, those 4 contributions, I get 42.84. Again, these are inches. Everything in here is inches per year. And this is our total answer. This is the average, I'm sorry, the total, I said that wrong, the total precipitation per year over our entire watershed. So there you go. That's the Thiessen method for estimating the average precipitation over a watershed.